In a three-phase system, the concept to understand is the phase relationship between voltages. They are often mentioned 120 degrees of separation between phases when discussing three-phase power is directly related to the 360 degrees of a complete cycle. However, when calculating line-to-line voltages from line to neutral voltages, the angular difference translates to a factor related to the cosine of the angle between them. The relationship between line-to-line voltage and line-to-neutral voltage in a three-phase system is defined by the square root of 3, which is approximately 1.73. This means that the line-to-line voltage will always be 1.73 times the line-to-neutral voltage. For instance, in a common three-phase system, you'll find the following voltage relationships. Phase A to neutral equals 120 volts. Phase B to neutral equals 120 volts. Phase C to neutral equals 120 volts. Phase A to phase B equals 208 volts. Phase A to phase C equals 208 volts. Phase B to phase C equals 208 volts. Notice that the line-to-line voltage, 208 volts, is approximately 1.73 times the line-to-neutral voltage, 120 volts. This difference is due to the 120-degree phase shift between each phase. This phase shift is critical to the operation and advantages of three-phase systems. The phase shift means that the voltage on each phase reaches its peak at different times. Specifically, there is a 120-degree difference between the peak voltage of each phase. This ensures that when one phase is at its minimum voltage, at least one of the other two phases is near its maximum. This characteristic allows three-phase systems to deliver power more efficiently and smoothly than single-phase systems. In a single-phase system, the voltage fluctuates between its positive and negative peaks, and the power delivered to the load also fluctuates. This can lead to inefficiencies and potential harmonic distortions. However, the phase shift in a three-phase system ensures that there is always at least one phase delivering close to its peak voltage at any given moment. As a result, the power delivered to the load is more constant and stable. This constant power delivery is one of the primary reasons why three-phase systems are used in industrial and commercial applications where high power and consistent performance are required. The overlapping of the phases provides a more consistent power supply compared to a single-phase system, where the power delivery drops to zero twice in every cycle. The 120-degree phase shift in three-phase systems is not arbitrary. It is carefully chosen to optimize the power delivery and minimize voltage imbalances. Other phase shifts could be used, but the 120-degree configuration provides the best balance between power delivery, efficiency, and system complexity. The concept of phase shift is also important in understanding how three-phase motors and generators work. Three-phase motors use the phase shift between the voltages to create a rotating magnetic field which drives the rotor. Similarly, three-phase generators use the phase shift to generate three separate voltages that are synchronized to deliver power to the grid. In summary, understanding the voltage relationships and phase shifts in a three-phase system is essential for anyone working with electrical power distribution or motor control. The 1.73 factor for calculating line-to-line voltage from line to neutral voltage, and the 120-degree phase shift between each phase are fundamental concepts that underpin the operation and advantages of three-phase power.